Alright, so far in the thermodynamics class or series of segments, we have been waiting for this very moment. This is the first big concept that we have, okay? First law of thermodynamics. We also refer to it as conservation of energy because at the end we talk about energy can be conserved, etc. Okay? And in the fluid mechanics class, for instance, we take this, we call this a conservation of energy and apply it to their fluidic system. So it's very related to thermodynamics, okay? But I mentioned this at the beginning of these segments, saying that energy can neither be created nor destroyed, right? But it can change forms, okay? But before I go ahead and write some equations that will help me with that, I want to take a more fundamental view and talk about this. Let's say that I have an income. It doesn't have to be dollar, I said dollar, but it's some type of a number, okay? 1,000 units, it doesn't have to be dollar. So, and let's say that this is my monthly income, and every month I'm spending, let's say, $1,100. So everything that I, spend adds up to $1,100. Some to the rent, some to the car payment, some to the educational loans that you have, food, etc. Right? Entertainment, whatever. So, okay, if this is an income to me, and this kind of like, let's say that this is my system, so this is coming in as 1,000 and this is leaving as 1,100, what's happening every month? So I have a deficit of this amount, right? 100. What I just explained is from finance point of view, but it is still the same thing that I will be discussing in here, except about these, dollar signs or any unit that you want. I'm going to look at the change in the energy, okay? And if I want to write this way, first law, here's what it says, okay? Total energy transfer into the system, total energy transfer. We talked about total energy transfer. What are the methods of it? I'll revisit it, but I have already discussed that. Total energy transfer, basically it's leaving the system, right? This is into the system, and total energy transfer out of the system, right? So now, okay, so far so good. What this inner total energy transfer into the system is like this, income, right? Income is this, and my system, I'm leaving this. So for instance, the right hand side will be minus 100 in this particular case, correct? And then we are going to say the change in total energy or total money in that particular example, okay? And I can do even better than that because I don't want to deal with these terminologies. I can call this in energy, out is equal to delta E of the system. Delta is highlighting that this is a change, okay? Okay, so this is really the first law. This is the fundamental first law that I'm talking about. The only thing is in here I explained this is, this number is this in, right? Right now this heat transfer, work, mass can be all part of the energy transfer, right? So I wanna discuss that. But before that, let me actually go ahead and discuss. Let's put some numbers. So I wanna say 2 minus 3 is equal to 1 kind of deal, right? Well, not mathematically, but you see where I'm going, right? In terms of the terminologies that I use. So let's look at 1. The 1 is E system. So let's discuss that for a minute. I had discussed that. If this is a simple compressible system, then I'm going to have the kinetic energy, I will have the potential energy, as well as the internal energy. These two are the macroscopic forms of energy. This is a microscopic form of the energy, okay? And this will be 1 half mv squared plus mgz plus m specific internal energy times the mass, okay? But now I'm looking at this delta E system, okay? So that what it means is I'm going to look at delta kinetic energy plus delta potential energy plus delta internal energy, okay? And then I can write this way: kinetic energy at D2 minus kinetic energy at D1, right? Plus I can have potential energy at D2 minus potential energy at D1 plus internal energy at D2 minus internal energy at D1. So that's pretty much it, okay? For so there are actually 3 terms in here. I say that the total change of energy, but these are going to be it. Okay, so let me ask you a question. If my system is stationary, what would the change in the system energy? It's a stationary system. Okay, stationary means that, looking over here, the velocity will be zero, stationary, so this term drops out. What about the potential energy? Yes, the system will have the potential energy. I have a segment on this as well. I had the ball here. Depending on the datum, I will be able to call the energy of the system as different values, because I will select different datum values, etc. But look what I'm doing in here. I'm looking at the energy difference. As long as I selected the same datum, right, one datum, like in here versus there, the potential energy change will be zero. So what I'm saying is that if my system is stationary, we use this often, okay, then delta E system actually will just be delta U, okay? That will be just delta U. So that will come in handy at some point in time, okay? And that's all I want to talk about the item number 1. And now I'm going to look at the item number 2 and 3, and I will basically discuss them together, because one is out, one is in, and so basically one has a positive, one has a negative in front of it, and you have it in the equation over there, okay? But let me repeat basically, because I said that for closed systems, right, if the system is closed, and I call this control mass, right, what I will have is this 2 and 3 will have two components, okay? I will have heat transfer and I will have work, okay? That's the two forms that I have. If I have an open system, for open systems, which we also refer to as controlled volume, right? Now I'll have heat, no question about it, same thing as work, but now the mass leaving or entering the system will bring its energy into the system or out of the system as well, okay? So if I write this mathematically, what I just said, because I have some letters abbreviated for each term, let's say E in minus E out, right? So this is term number 2 minus term number 3 will be Q in, Q is the heat transfer, right? Q out plus work in minus work out. Let's write the most general one. E mass in minus E mass out, okay? And let's put a note over here. So this particular term, 0 for control mass, right? Because the mass, there's no mass transfer, so it cannot carry its energy out or into the system, okay? And if I'm looking at the units, so that's pretty much it, you know, in terms of what I want to cover. Once I cover all the stuff that I did, the rest, covering the first law, is kind of, you know, like adding a couple terms and equating to some other. So it's really a high school or lower level mathematics is required for this particular case, okay? The big elephant in the room at this point is the U though, okay? So this, I said delta U. How am I going to calculate the delta U? I'll address that in module 3. So far, we're not really dealing with that, okay? So what's the units so far, right? So I have dealt with the energy, and energy units, if I have like a pair, let's call it the SI British gravitational pair, you're going to have joule or BTU, and most of the time it's going to be kilojoules, because joule is kind of small, okay? And I can also write this in rate form, right? This particular equation, then it's going to be E dot in, energy rate entering minus energy leaving, will be Q dot in, which is heat transfer rate. This is power in minus power out, and mass transfer rate in minus mass transfer rate out, okay? So what will be the units in that particular combo that I write over here? This is going to be watts, right? W will be sufficient, and BTU per hour will be another one, or if you want to be consistent with this type of writing, this can be said joule per second as well, okay? I can also write this, you know, I'm running out of energy, pun intended over here, is that I can also write this in, you know, this equation in unit mass, right? Because you see, going up here, I said I didn't write it, probably I will at the end of the day, but you see over here, so I can divide everything by mass. This goes away, this goes away, this goes away, right? So why don't I write it, because I might as well, right? E in minus E out will be delta E of the system. Okay, so this E in will be basically everything that you see in lowercase, well, not here actually, here, but lowercase q, lowercase q, lowercase w, lowercase e, and the right hand side delta E system. And I want to write that because it's going to be v squared over 2 plus gz plus the internal energy, or rather more specific internal energy. Okay, and the units this time around in terms of the pair is joule per kilogram. This was joule per second, right? And I'm gonna have BTU per pound mass. That will be my unit pairs. Okay. So the only thing that I want to cover, and sometimes some resources are finishing over here, but if you remember, I had a convention, sign conventions, right? So just give me 1 second, let me copy paste it over here and I'll be right back, okay? It will be more convenient. I don't want to rewrite the same thing I did, okay? Okay, so I'm back. So this is from the previous segment. I'll put the link over here as well at the right hand side top. But the point is this: I have, as long as the heat is coming into my system, I put positive. If it's leaving, it's negative. Fine, good. Here's the problem we talked about. If I have the work out, I'm going to put it as positive. And I'm going to work in is going to be the negative, right? So then, okay, so I can still, for a closed system, because it's a closed system, at the end of the day, it doesn't matter. E in minus E out can easily be written this way. And as long as you know what you're doing, this is just perfectly fine, okay? W in minus W out, right? Because when I have a work input to my system, work done on the system, what I will have is I will have increased energy, right? When I have the work done by the system, this will decrease the energy of my system, okay? So this is fine. But you can see in here, we have an issue. So this is positive, so it's supposed to be negative. So then I need a negative in between those two, okay? So if I write this way, and we use this in fluid mechanics this way as well, Q net minus W net, okay? You can see over here what is happening. So this W net is defined as basically work out minus work in, isn't it? Because if you put a negative this, you get that equation. And on the other hand, Q net is defined as Q in minus Q out, okay? You may not like it, you might not have to use it. As long as what you're doing, I'm okay with that. Some resources and professors call it a plus sign over here, and they just define this as this, which is fine. There's nothing wrong with that. Only the problem with that approach is the FE exam follows this format, okay? And let's also talk about a cycle. We talked about what a cycle is. So basically, I start from this state. I go to state number 2, then I go to state number 3, and then I come right back to state number 1, right? So in this kind of case, you can see as looking over here, I'm looking at the energy change, right? The energy change, so looking in here, so the right here, the change will be 0 because the end state and the initial state is the same. So 3 is equal to, well, rather 4 is equal to 1 in this particular case. So if you want to call this one as 4, like 1 to 2, 2 to 3, 3 to 4, but the 4 is equal to 1. So then delta E will be 0. So what does this mean about that equation that I write over here? This is another convenience by putting a negative sign, is that you're going to get Q net minus W net will be equal to 0. And if I move one of them to the other side, I will get Q net will be equal to W net, right? The net, basically the net heat transfer coming into my system will be coming out as the work output from the system, okay? So this is, we use this often as well, okay? All right, so that's all I have about the first law. Not a lot. It's kind of simple after we discuss all these. So now I'll be back with an example to illustrate how these all come together, okay? Thank you for watching this.